Hello, welcome students. I am Rekha Thorat, Associate Professor. Today we consider next theorems of this Unit 2. Here in this chapter there are more theorems. Today we consider theorem 6. Statement of this theorem is if H is a normal subgroup of a group G and K is any subgroup of group G, then HK equal to KH. That means H is normal subgroup of G and K is any subgroup of G, then HK equal to KH. We have proved that HK equal to KH. In this proof, the proof of this theorem, let us assume that G be a group and H be a normal subgroup of G and K be any subgroup of group G. To prove that HK equal to KH, let small hk belongs to hk, where h belongs to h and k belongs to k. Here we can write hk equal to k into k inverse into hk. Since k into k inverse is identity element, which is equal to k into bracket k inverse into hk bracket complete by associative property. But H is normal subgroup of group G. Since H is normal subgroup of group G, therefore for H belongs to H and K belongs to G, this implies K inverse into HK belongs to H, and this implies HK equal to K into bracket K inverse HK bracket complete belongs to KH. Hence, HK is contained in KH. That is, for H belongs to H and K belongs to G, K inverse into HK belongs to H. This implies HK belong equal to, we have written that HK can be written as K into K inverse into HK, and by associative property this is equal to K into bracket K inverse into HK bracket complete, which is belongs to KH. Hence HK is contained in KH. Denote it as number 1. Again, it is assumed that KH belongs to, small kh belongs to KH, where K belongs to K and H belongs to H. We can write small kh equal to small kh into K inverse into K, and by associative property this is equal to, in bracket, KH K inverse bracket complete into K. But we know that H is normal subgroup of G. Therefore, H belongs to H, for H belongs to H and K belongs to K. This implies, since H is normal, KH K inverse belongs to H. And this implies KH equal to K inverse H in bracket K inverse HK bracket complete into K, which belongs to HK. Since H is normal, we have, for H belongs to H and K belongs to G, KH K inverse belongs to H. This implies KH equal to KH, which is equal to, Since it is normal, Hk equal to Kh. So that Kh equal to Hk, K inverse into K. And by associative property, we have taken these three terms in first bracket. Bracket complete into K. And this belongs to Hk. Since by normal property, this belongs to H. And this is K. This belongs to Hk. Thus, Hk is contained in Kh. Denote it as number 2. Thus, from 1 and 2, in first part we have proved that Hk is contained in Kh. And in second part we prove that Kh is contained in Hk. From 1 and 2 we prove that Hk equal to Kh. Thus, if H is normal subgroup of group G and K is any subgroup of a group G, then Hk equal to Kh. That means in this proof, first we assume that G be a group and H is normal subgroup of G and K be any subgroup of G. And we prove that Hk equal to Kh. And for this proof, we assume that small hk belongs to H and small kh belongs to H. And by using property K into K inverse equal to U and multiplying it, this belongs to HK, which is contained in KH. And again we have assumed that small kh belongs to KH. Again we have used for K belongs to K and H belongs to H, and we have used this property again by multiplying it as K inverse into K and associative property, and we assume that KH is contained in HK, and from 1 and 2 we prove that HK equal to KH. Now we consider one theorem, and statement of this theorem is, if N is a normal subgroup of G and H is any subgroup of G, then NH is a subgroup of G. For objective question is, if N is normal subgroup of G and H is any subgroup of G, then NH is a subgroup of G. Thus, you must stress on this statement. Let us consider the proof of this theorem. Let G be a group and H be a subgroup of group G. Let N be a normal subgroup of group G and H be any subgroup of group G. Therefore, by theorem, just we have proved that if H is normal subgroup and K be a subgroup, then HK equal to KH. Using this property, we have here G is a group and N is normal subgroup. Instead of K, here N. So that we must get NH equal to HN by this theorem. Now, N and H are subgroup of group G such that NH equal to HN. Therefore, by theorem 5, NH is also a subgroup of group G. Theorem 5 is, HK is subgroup of G if and only if HK equal to KH. By this theorem, NH, the N and H are subgroups of G such that NH equal to HN. Hence, NH is a subgroup of group G. Now we consider one theorem. Statement of this theorem is, The product of any two normal subgroups of group G is a normal subgroup of G. Here, product of any two normal subgroup of G is dash dash. It is again a normal subgroup of the group G. Now we consider proof of this theorem. Let G be a group and also assume that H and K be normal subgroups of this group G. We have to prove that HK is a normal subgroup of group G. That means if any two product of any two normal subgroups of G is again a normal subgroup of G. We have to prove this. Here we have assumed that H and K are normal. So we have to prove that HK is a normal subgroup of group G. Now, as K is normal subgroup of G and K is a subgroup of G, and since H is also a normal subgroup of G and K is a subgroup of group G, we must have HK equal to KH. We have proved this in previous theorem. Now, H and K are two subgroup of G such that HK equal to KH. Therefore, HK must be a subgroup of group G by previous theorem. Now, to show that HK is normal, we have proved that HK is subgroup. Since both H and K are normal and satisfy the property HK equal to KH, so that HK must be a subgroup of G. We have to prove that HK is normal subgroup of G. To prove this, let us assume that let G be any element of G and HK be any element of HK, capital HK. Then H, small h belongs to capital H and small k belongs to capital K. Then we have G into bracket small hk bracket complete into G inverse equal to, in first bracket G inverse bracket complete into, in second bracket G inverse bracket complete, and this belongs to HK since H and K are normal. Normal means G inverse belongs to HK, G inverse belongs to HK. This property satisfied. So that HK is a normal subgroup of G. Since here H is normal subgroup, G inverse belongs to H. Also, since K is normal subgroup, G inverse belongs to K. Here we have considered product, that is G into bracket HK into G inverse equal to G in first bracket G inverse bracket complete, and in second bracket G inverse bracket complete, and this belongs to HK since H and K are normal. This is possible since H and K are normal subgroups of group G. Hence, HK is also satisfied this property, that is G into HK into G inverse. This is also belongs to HK. That means property of normal subgroup is satisfied by this HK. Hence, HK is a normal subgroup of this group G. Thus, product of any two normal subgroup, H and K are normal, then product of normal subgroups of group G is again a normal subgroup of G. Thus we have proved the theorem. Thank you.